All right, let's do this thing. But before we get started, there are a few things that I just gotta say that are kind of ridiculous. Number one is one of my friends emailed Jay Cummings, author of this book, and told him about the series that I'm making. And the mad lad replied to the email and said he was looking forward to seeing more of it, which is absolutely insane. Second insane thing happened is that somehow my video has 29 views and one of them is this guy. That's certainly one of the things that's ever happened to anyone. Let's go ahead and get started. I'm not really sure whether before I do the problems I should give like an overview of the definitions, like basically go through what the chapter of the book goes through before the exercises, to give people who may not be so familiar like an understanding of what actually I am doing. So if you're someone that is looking at this, the math I'm doing, and you're like, none of this makes any sense, and you want to keep watching for some reason, then I guess tell me that, and I'll make some kind of a preparer. That's not really a great word. Some kind of preparatory material for understanding the videos, like relevant definitions and whatnot. But last time I left off with 1.11. You may recall that as the subject of the hilarious think timer bit, but I did it right, I'm pretty sure. And now I'm on to 1.12. Oh wait, before I am though, there is an error in the last video, at least one that I found. Hold on, let me find it. Here we go. 1.2. I am asked to decide the truth value of this statement, and I did it wrong at first. I took z to be y minus x over 2, which is not the midpoint of y and x. This is. So that's one error. It's a great start. Question 2. Really showing my chops here. And let's get started. 1.12. Let F be an ordered field. A, B, C, and D are in the field with A less than B and C less than D. Show that A plus C is less than B plus D. Okay. A less than B means that B minus A is in the positive elements of the field. Likewise for D minus C, that's in the positive elements of the field. Then, if I use like all of the first three axioms, I can write B plus D minus A minus C as B plus D minus A plus C, which is, I didn't actually need this step. Like I could have just done commutativity to switch this guy around, and then that would have been fine. But B minus A plus D minus C is in P because the positives are closed under addition. So that means A plus C is less than B plus D. What? Oh, yeah. Because B plus D minus A plus C, which is equal to this thing, is in the positives. Yeah. So this thing is in the positives. So B plus D is greater than A plus C. Or, yeah. Oh, confused myself there, but no, we're good. Also for here, I used axiom 6a, which I think is closure of positives under addition. I used associativity, commutativity, and distributivity here. I used distributivity here specifically when I pulled this minus out and turned that into a plus. And then part B is prove that it is not necessarily true that AC is less than BD. A counterexample is pretty easy to craft in the real numbers. If we take A and C to be -2, then we have A is less than B and C is less than D if B and D are 0. But then AB is 4, which is greater than 0. 0 equals BD, 0 times 0. Okay, then we're on to 1.13. There it is. Let A and B and epsilon be elements of an ordered field. Show that if A is less than B plus epsilon for every epsilon greater than 0, then A is less than or equal to B. I started this the way you prove this in the reals, which is you go to like contrapositive. You suppose A is greater than B, and then the half of the distance between them works as an epsilon for A still greater than B plus epsilon. But we're not in the reals, so I can't really do that. Then I try to just let epsilon be A minus B over 2, and I'm like, I don't really want to use numbers if I can get away with it. I want to get away with like just field elements. And so I let C be the number after 1, and then I was trying to show that like C inverse minus B inverse was small enough in epsilon to make this still true, and oh boy, it was a big mess. But on the next page I do it pretty convincingly. So if we suppose to the contrary, so we're supposing that for every epsilon 0 this holds, epsilon greater than 0 this holds, then suppose to the contrary that B is less than A, that A minus B is positive. Since A minus B is positive, we should have that B plus A minus B minus A is positive. But B plus A minus B minus A is B plus A minus B minus A equals 0, which is a contradiction. This is, I didn't really explain it well in the paper or on this proof, but since A is less than B plus epsilon for every epsilon greater than 0, it's every positive epsilon, and then I suppose B is less than A. That means A minus B should be positive, which means that B plus something positive minus A should also be positive. But B plus A minus B minus A is 0, which is a contradiction. So it can't be that B is less than A, which means that A is less than or equal to B. Much easier. I guess I could make this clear. Let's like mark this and bring it down here. Since A minus B in P, and for every epsilon in P, B plus epsilon minus A is in P. There we go. That makes it clear. 1.14. There it is. Shorter. And pretty easy to get done. Each case is like one line. If we have A and B are real numbers, then absolute value of AB is absolute value of B times absolute value of A, I guess. I don't know why I put it like that instead of absolute value A times absolute value B. Oh, it still holds because of commutativity. So I went ahead and I said it should be obvious. This should be obvious to be true if A is 0 or B is 0. So I didn't even consider those cases. So there are now 3 cases, 3 with an asterisk, because their sign can either be both positive, both negative, or their signs can be different. And the proof is the same no matter if B or A is the negative one. So I just went with A being the negative one. Okay, absolute value of AB. Since A and B are both positive, then this is positive, which means it's just itself. A is equal to the absolute value of A because A is positive, and B is also equal to the absolute value of B because it's positive. Done. Case 2, absolute value of AB is still AB, since if they're both negative, then their product is positive. And AB equals this, because absolute value of this is positive, absolute value of this is positive. They're the same. And then case 3, which is the only complicated one, since we have this, AB is negative, so absolute value of AB is the opposite of AB, which is the opposite of A times B, which is absolute value of A times absolute value of B. There you go. 1.15. This one, it was a lot of work. It was a lot of ink. It took a lot of time. It's kind of like algebra stuff. Wasn't too huge a fan, but like I get it. So I'm given some kind of absolute value equation, and I'm supposed to find all the values that fulfill it. So if absolute value of x minus 4 is equal to 7, that means this is either positive or negative 7. The x values that work for that are 11 and 13. And then if the absolute value of x minus 4 is less than 7, there's like 2 ways to think about this. You can either have the ball centered at 4 of radius 7, or you can like do it algebraically like this. And then everything from -3 to 11, the open interval, works since we have strictly less than. The distance between x and -2 is smaller than 1. So that's the ball. I messed up the ball though. I put the radius first in the first time. And so that's wrong. This is the right ball. And this is where it actually started to get interesting. Absolute value of x minus 1 plus absolute value of x minus 2 is greater than 1. This means the distance from x and 1 plus the difference from x and 2 is bigger than 1. There's 2 ways I thought about this one too. Anything in here isn't going to work because the distance from 1 to x and then from x to 2 is going to be just the distance from 1 to 2, which is 1. But if anything's outside of that, outside of this little ball, it's going to work. And the algebra kind of confirmed that too. I used the triangle inequality here to smush these absolute values together. And it ended up spitting out good math. I'm not sure if that's like an essential property of what I was doing or if that was just like an accident. Then we have the distance between x and 1 plus the distance between x and -1 is greater than 1. That works for every x. That's always true because the distance here is 2. So if you pick anything here, then this distance is going to be 2. If you pick anything out here, then this distance is going to be greater than 2. And if you pick anything over here, then this distance is going to be greater than 2. So it's actually always at least 2. That's how every real number works. Then we have distance between x and 1 minus the distance between x and -1 is greater than 1. This actually took a a little bit of thinking, to be honest, but eventually I came up with everything less than negative a half. Because if I think about this, the distance from here to here is 3/2. The distance from here to here is going to be a half. So this minus that is going to be equal to 1. Then anything past here, this is just getting bigger. And this gets smaller and then gets bigger. And they get bigger at the same rate. Anything out here isn't going to work because the distance between x and 1 is always going to be smaller than the distance between x and negative 1, because distance between x and 1 is that guy, x and negative 1 is that guy. And then g, absolute value of x minus 1 times absolute value of x plus 1 equals 0. That's true if and only if one of these is 0. And so there's actually only two values because 1 and negative 1 are the only things that work. You go ahead and check that yourself, I guess. And then we have absolute value of x minus 1 times absolute value of x plus 2 equals 3. We can use a property of absolute values to squish these together. Then we get a quadratic equation inside of this, which means this is equal to 3 or negative 3. You can do the quadratic formula on both of them. It turns out this one has no real solutions. But both of these, I checked them with Wolfram Alpha, and they both came out to be 3 when I plugged them into here. So I'm going to call that a win. 1.16. This one looked pretty intimidating from the start, but wasn't actually that bad. Prove that max xy is this formula up here, and that min xy is a similar formula with a minus instead of a plus here. And then this quickly makes sense if you think about it as if you just split this 2 under both of these. So this is x plus y over 2 minus absolute value y minus x over 2. This is their midpoint, and this is their distance. So you get to the midpoint, and you go either half the distance towards one of them or half the distance towards the other one. Either way, you land on one of the points, and this minus here changes which one of those that is. So we have a few cases. Y is greater than or equal to x, then x plus y plus absolute value of y minus x over 2 is x plus y plus y minus x, because this is going to be greater than or equal to 0, which you can cancel out the x's and you get 2y over 2, which is y, which is the maximum of x and y, because again, y is greater than or equal to x. And I also did the min here, so same kind of deal. This is greater than 0. Can cancel out these y's. You get 2x over 2, which is x, which is the minimum, because x is small. And you have case 2. Y is less than x. It's the same thing, but the other way around. Pretty easy. And then it asks us to find a formula for max xyz and min xyz. And at first, my thought was, all right, let's take the average of all three of them and add something to it. But no, that wasn't going to work. Something much simpler was realizing that one of these is going to be in between the other two. So actually, we can do the same trick again. We can just find the distance. We can just find the midpoint between the outer two, and then do the same thing. And the way this kind of like manifested itself, I guess, was if you note that max xyz is max x, the max yz, then it's pretty easy because we already have a formula for the max of two things. We just put x and the other thing in there, and then this has a formula, so you put that in there as well. Minimum is similar. Minimum of xyz is minimum x, minimum yz. So you do the minimum formula and you put minimum yz, that formula, into where it would say min. Cool exercise. Okay, next we've got an induction question. Well, I guess it didn't specify induction, but this is the kind of thing induction was made for. If a is less than b, then a to the n is less than b to the n for every natural number n. By induction, we start with the base case. A to the 1 is less than b to the 1. Done. Pretty easy because a is less than b. Free money. Then we move on to the inductive step. Suppose a to the k is less than b to the k. Then a to the k times a is less than b to the k times a is less than b to the k times b, which means a to the k is less than b to the k, implies a to the k a is less than b to the k a. Wait, what? Why'd I write this so weird? Oh, here we go. A to the k times a is less than b to the k times a is less than b to the k times b. So by transitivity, a to the k plus 1 is less than b to the k plus 1. And this is true because a to the k, this underlined bit, is true because a to the k is less than b to the k, which means a to the k times a is less than b to the k times a. And b is greater than 0, which I guess I didn't put up here, but I did. It is part of the problem. It is part of the problem. B is greater than 0 means b to the k is greater than 0. And that means since a is less than b, b to the k times a is less than b to the k times b. So all these hold. This actually is the big guy that proves the inductive step. So then we're done. 1.18. Prove the big triangle inequality. N-term triangle inequality. I can do that. Can in fact do it by induction also. Ignore this. The induction a is less than or equal to a. Also, the triangle inequality normally holds. Yeah, so here's where the proof really starts. All that before is just nonsense. Base case, absolute value of a is less than or equal to absolute value of a. That's true. But we also have, I did the regular triangle inequality, just like, I guess, in case it wasn't enough that this was n equals 1. I don't know why it wouldn't be, but, you know, that's what I did. Then we suppose that a big triangle inequality holds, and we want to suppose that it holds for k plus 1. Then we've got our big sum here. This is equal to our k plus 1th sum. This is equal to our k term sum plus the k plus 1th term. Which is less than or equal to the absolute value of the k terms plus the absolute value of the k plus 1th term. That's just normal triangle inequality. That's a real number. That's a real number. So you can split those. Then by the induction hypothesis, this guy, all of this is less than or equal to the k term sum is less than or equal to the absolute value of each term of the k term sum together. Then you add on the k plus 1th term at the end, and then voila, we did it. We've shown an nth term triangle inequality. There's another inductive question. (1.19). Prove that the sum from k plus 1 to n of 1 over k times k plus 1 is n over n plus 1 for all n and n. Okay, go ahead and prove the base case. For n equals 1, 1 over 1 times 1 plus 1 is 1 over 1 plus 1, which is a half. Good. Base case done. Now we go into the inductive step, which I crossed this out because I messed up the sigma notation and I got all confused. But here it is really. If we suppose that this holds, which is the beginning of the induction step, that's the induction hypothesis, we need to show that it holds for m plus 1. So I can split this into the m terms and then add on the m plus 1th term, which is going to be 1 over m plus 1 plus m plus 2 times m plus 2, because this is m plus 1 plus 1, which makes it m plus 2. This is equal to, since this is equal to this guy, I can just replace him. This is m over m plus 1 plus 1 over m plus 1 times m plus 2. I get a common denominator by multiplying this by m plus 2 over m plus 2. So I get m plus 2 plus 1 over m plus 1 m plus 2. And I get some quadratics, which I can factor out and then cancel off this m plus 1. And I get m plus 1 over m plus 2, which is m plus 2 famously is m plus 1 plus 1. And that's what we want to show. We'll just put an m plus 1 here instead of an m. And that's it. We're good. We did it. All right. Determine which natural numbers have the property that the square root of n is irrational. Now we already know that the square root of p is irrational. Oh, what? Square root of p is prime. No. Square root of p is irrational, where p is a prime. By the proof that root 3 equals, that root 3 is not rational. That proof wasn't specific to 3. It works for any prime. So prime numbers are a collection which have the property that square root of p is irrational. Then if we have a number that is a non-perfect square composite number, the same argument that proves root 2 is irrational implies that root p1 times p times all the way up to pm is irrational. Okay. If n has any even powers in its prime factorization, then it can be written as q times root p1 times up times pn, where we can just pull the even powers out, because that means there's something squared, and the square root of that is just the thing. So we can pull out all the terms with even powers. I just represented that by a q here. Q would be rational because it's an integer. And this is irrational. And we already know that irrational times an irrational is irrational. I went ahead and proved that root p1 times blah 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 times pm is irrational. This might be the one I'm least confident about of this set. 1.21. F from x to y is a function, and a1 and a2 are subsets of x. I'm going to show that. The function applied at an intersection is contained at the intersection of the function applied at the sets. So suppose that x is in f of this intersection. Then there is some y in the intersection such that f of y equals x. Since y is in a1 and y is in a2, then f of y is in the image of a1 and it's in the image of a2. That's what it means to be in the image. So f of y is in this and this, so it's in the intersection. And fy also equals x. So then that's one-way containment. X is an arbitrary element in here. We showed that it's in here. So everything in here is in here. Uh, 1.22. Supposed to give an example of a function where these are not equal. And this didn't take that long. I'm like, well, if I have two functions and if I have like two sets that only intersect at like one point, then surely I can get some wackiness going. So if I let a be 0 to 1, the closed interval, and b be -1 to 0, the closed interval. And I define f from -1 to 1 to r, defined by f of x equals x squared. This is actually, I guess this is an extension of the function, which is fine because these have the universal extension property. Anyway, I just drew the rest of kind of more of x squared to get you like knowing what was going on. So f of a intersect b is just 0. So it's going to be this single point. F of the interval 0 to 1 is all of these values here. Same for f of the interval b. It's all of these values here because it goes along and it picks up all of these until it stops right here. F of a goes along all of these and picks them all up until it stops right there. And so there we go. F of a intersect b does not equal f of a intersect f of b, because this is the singleton set 0 and this is the interval from 0 to 1. Pretty good. 1.23. Assume that a and b are both bounded above. Prove that sup a is less than or equal to sup b. Assuming that a and b are some kind of ordered set, like the naturals, I guess. So that sup a and sup b like makes some sense. Okay, I did some stuff. I tried to go by contradiction. I was like, screw it. If b, little b, is an upper bound of big B, then b is an upper bound of a. I proved that here, but just keep following. Particularly, sup b is an upper bound of a. And that's it. That's all you need. I'm pretty sure. Because if you have an upper bound, if you have sup b being an upper bound of a, then the least upper bound of a cannot possibly be bigger than sup b, because then sup b would be a smaller upper bound. Pretty simple. I also proved the underlined thing here. B is an upper bound of That's a B. It's a big B. Then for every B prime in big B, B prime is less than or equal to B. That's what being an upper bound means. Since A is in B for every A in big A, then for all A in A, we have A is less than or equal to B. Right? If A is in A, then A is in B. Then for every B in B, it's less than or equal to B. So if B is an upper bound of big B, then B is an upper bound of big A. Okay. Suppose A subset of R, has a maximal element M, and B, which is also a subset of R, has a minimal element M, little m. Prove that sup A is equal to big M. Okay. We need to prove two things. M is an upper bound of A, and M is the least upper bound of A. I think I did this. Well, let's find out. M is an upper bound of A. Super easy, given that for every x in A, x is less than or equal to M. That's done. So M is an upper bound. Now the hard part. We can either prove that every other upper bound is no smaller than M, or that everything smaller than M isn't an upper bound. Okay, so I chose to let n not equal to M be an upper bound of A. Then by trichotomy, either n is less than M or n is greater than M. If n is less than M, then n can't be an upper bound. So actually, n has to be greater than M. So any upper bound that's not M is greater than M, in fact. So M is the supremum. Could have also just as easily have let n be any upper bound and shown that n cannot be less than M, because then it would be less than something in the set. The proof is similar for B. Prove inf B equals M. M is a lower bound of B. That's easy enough. And if n is a lower bound of B, then M is not less than n, by a similar argument to A. Okay, now we have 1.25. How many of these did I do? Okay, it looks like this is close to the last one. A non-empty set A contains finitely many elements. Prove by induction that A has a maximal element and that max A is in A. I went ahead and guessed that the set was probably ordered by something, so that max A made sense. I went ahead and said it was ordered by less than or equal to, and I just said it was totally ordered because it's a totally ordered set would be the most similar thing to R, which is also totally ordered. I don't know if this is like a mistake in the book, but it doesn't say anything about the A being ordered in the exercise, so I just kind of imposed a total order on it, and then I solved that version of the problem. Okay. Use induction. Cardinality of A is 1. The only element is a maximum of A, because A is less than or equal to itself by reflexivity of the order. That's part of the definition of an order. There's nothing more I can do to convince you. Now for the inductive step, suppose every set A of cardinality n has a maximum in A. Okay, then let A tilde be a set with n plus 1 elements, and let B be in A tilde. Any B at all, doesn't matter. And consider A tilde take away B. This is a set with n elements, and so it has a maximum in A tilde. Let C be the maximum of A tilde minus B. Then take C tilde to be the max of C and B. C tilde is equal to max A tilde, And this can be seen to be true because if c tilde equals c, this guy over here, then for every x in a tilde minus b, x is less than or equal to c. Then since c tilde equals the max of a tilde minus b, then b is less than or equal to c tilde is equal to c. If c tilde equals b, then for every x in a tilde minus b, x is less than or equal to c is less than or equal to b. So a set with n plus 1 elements has a maximum, and max a is in A. Okay. Prove that n is complete. I am not sure if I finished this one or not, but I'm going to go ahead and show it to you anyway. There exists an m such that for every a in A is less than or equal to m. All right, I didn't do this one. Pretty unlucky. All right, give me a moment. All right, here it is. 1.26, n is complete. I ignore all this. None of this matters. Well, maybe it does matter. I went ahead and supposed that I took the set of all upper bounds of A. Then I said it has to have at least one by well ordering. I'm like, I didn't really show that the upper bounds of A are in the naturals, did I? So I went ahead and I did it in a way I think is right. Let A subset of the naturals, be bounded above. By the last exercise, A has a maximum, and max A is in A, which is a subset of the naturals. We recall this. A has finitely many elements, so A has a maximal element, and max A is in A. A has finitely many elements because if A is bounded above, then there are only so many elements between 1 and the upper bound. There's finitely many between 1 and the upper bound. So we want that max A is sup A. That would make this super easy. So if I let M be an upper bound of A, then M cannot be less than max A, because max A is in A. If M is an upper bound, M has to be greater than or equal to everything in A, including max A, which is in A. So if M is an upper bound, then M must be greater than or equal to max A. Pretty simple. Max A is equal to sup A, which is in A, since max A is in A. A is a subset of the naturals, so sup A is in the naturals. So any set, A subset of the naturals, bounded above, has a supremum in the naturals, so n is complete. So I ended up fixing my proof for 1.2. Basically, it boiled down to proving that a finite product of distinct primes was irrational, which I have managed to do. I went ahead with a base case. Root P is irrational. That's well known. It's got to be the case. So then I went ahead and did the inductive step. I suppose that a M long finite product of distinct primes is irrational. Then root an M plus 1 product of distinct primes. I ended up separating this out. I don't think I actually needed to. To prove this is irrational, I went ahead and did the old contradiction. Then suppose there was some M and N. God, I'm really bad about this. I'm really bad about like saying where my stuff is in. N is not 0. Suppose M divided by N is equal to this product. Then M squared equals the product times N squared. Then Bm plus 1 divides M squared, because there's a whole number you can multiply Pm plus 1 by to get m squared. There it is. It's this times this. Since pm plus 1 divides m squared and pm plus 1 is prime, pm plus 1 also divides m. So there's an integer L where pm plus 1 times L equals m. So I plug that in for m and I get pm plus 1 squared. L squared is p1 up to pm plus 1 times n squared. So I divided the pm plus 1. I got pm plus 1. L squared is p1 up to pm n squared. Now, pm plus 1 divides n squared because all of these are prime, so their only divisors are 1 and themselves, and these are distinct primes, so this is none of these, so this doesn't divide any of these. So since p times something is equal to all of this, pm plus 1 has to divide n squared, which means that pm plus 1 also divides n, which is a contradiction of GCD mn equals 1. Right, because, okay, let me like, pm plus 1 has to divide this whole product. So pm plus 1 has to divide, since it's a prime, has to divide either this or p2 or p3 yada yada up to pm or n squared. So it has to divide n squared because it doesn't divide any of these. I think that's it. Yeah, that's it for today. See you next time, I guess.